Hello again. Have you ever been fishing and observed the following kind of curiosity? Um, I'm not a great fisherman, but I've noticed that when I look out of the boat and I see a fish down there, I think it's in that position in the water, but actually it's in a different position. The fish seems to be at a certain place, but due to the concept of refraction, its actual position is quite different. And refraction in Snell's law can be used to explain this curiosity. It turns out that when light waves are traveling in a transparent medium and they strike the surface of a second transparent medium, like from air to water, they tend to bend in order to follow the path of minimum time. And this tendency is called refraction and is described by the famous Snell's law of refraction. Let's look at this picture and I'll try to describe Snell's law for you. Imagine L is a line that separates medium 1 from medium 2. You can think of it as, say, the surface of the lake. And somebody is up at position P and looking down, and then there's a fish or some creature in the water at position Q. And the light goes from P and strikes the line L at, say, a point O. The point O is a distance x on the right and a distance y on the left from the projections of P and Q onto L, as labeled in the graph. And furthermore, the line from P to O makes an angle of theta 1 with the vertical through O, and makes an angle of theta 2 through the vertical at O, the line from O down to Q. And assume that x plus y is a constant. We'll call it A. That's a constraint. X plus y is a constant. So what's Snell's law given this picture? It's a very simple equation. Sine of theta 1, that's that angle that it's made with the vertical there, over V1 equals sine theta 2 over V2, where V1 and V2 are the velocities of light in the two media. Well, that's really a fantastic law. Wow, so simple. And you see it in physics courses all the time. Well, we'll be able to derive this law in this lecture using Lagrange multipliers. Won't that be interesting that we can derive Snell's law using Lagrange multipliers? Well, what about these Lagrange multipliers? Let me step back a bit and remind you how they work. We're given some function f and some function g having continuous first partial derivatives. As I said many times, nice functions. And we suppose f has a maximum or a minimum, in other words, an extremum, at a point x0, y0. And suppose that extremum lies on a constraint curve, g of xy equals c. And of course, the gradient of g cannot equal 0. Okay, so given that setup, it turns out that the gradient of f is a multiple of the gradient of g. In other words, gradient of f equals lambda gradient of g at that maximum point or minimum point. And that's the heart of Lagrange multipliers. Here's how you do a Lagrange multiplier problem. To find the maximum or minimum of a function, f, subject to a constraint g, where g of xy equals a constant c, solve the equations gradient of f equals lambda gradient of g together with the constraint equation g of xy equals c. And as we saw in the last lecture, calculating the gradients is a calculus topic, not too difficult. It's just taking some partial derivatives. And then by equating those corresponding I components, j components, and perhaps k components, you get this system of algebraic equations. And you try to solve those equations for x, y, and lambda. And then you can evaluate f at each of your solutions. Up to now, we've only had a single solution, and you'll select the maximum and minimum. And as I said before, this works for 3 variables, more variables, and for more constraints. You can have 2 Lagrange multipliers in some problems. All right, before we go to Snell's law, let me pause here for a moment and solve a maximization problem that we saw earlier. I really like to do problems twice. I like to show one technique and then in a later lecture show another one. There are various advantages to that. You can then sort of select which method you prefer. You can see how these methods give the same answer and yet look quite different. In mathematics, there are many ways of solving a problem. There's not just one path to the truth. Okay, this problem we solved in lecture 7, and it was mailing a package. We wanted to maximize the dimensions of a box in order to send it in the mail or some delivery service. And there was a restriction in this problem. So let me remind you what the problem said. It said that the sum of the length and the girth, remember the girth is the perimeter of a cross-section, of a package carried by a delivery service cannot exceed 108 inches. And we want to find the dimensions of the rectangular package of largest volume that can be sent. So we want to maximize a volume, but we have a constraint. Length plus girth is 108 at the most. So here's our setup in the variables. Let's assume that x is the length of our package and y and z give the girth measurements. So the girth is 2y plus 2z. Okay, we want to maximize the volume, xyz. That's the volume of our package. And the constraint is that x, the length, plus the girth, which would be 2y plus 2z, equals 108. That's our constraint. Well, there are many, many sizes of packages you could imagine here. Let's play with some packages for a moment. You're working for this delivery service and you're saying, gee, I'd like to construct a package of maximum volume. Maybe the package would have the following dimensions: 21 by 21 by 24. That's nearly a square package, isn't it? The dimensions are almost the same, 21, 21, 24. Now, let's check to see if it meets our requirements. What's the girth? Well, 21 plus 21 plus 21 plus 21. The girth is 84, and the length is 24. Add those up, 108. So I've met the requirement that girth plus length is 108. Let's see what the volume of this nearly square package is. Well, it's 21 times 21 times 24. Put my calculator out there, and I get 10,584. Well, another employee comes along and says, no, I can do better. I'm going to use a package with the following dimensions: 15 by 15 by 48. Quite long with not much girth. But let's see if it meets the requirements. The girth is 4 times 15 or 60. The length is 48. Yeah, girth plus length is 108. So it's a legal package. What's the volume now? 15 times 15 times 48. Oh, now that's 10,800. That employee's done a little bit better. But of course, along comes the employee that studied Lagrange multipliers, and that employee is going to do even better. So let's see how it works. We want to maximize the volume function v equals xyz. The constraint, g of xyz equals x plus 2y plus 2z equals 108. We need the gradients. Gradient of the volume is yzi plus xzj plus xyk. How did I get that? I differentiated v first with respect to x, then with respect to y, then with respect to z. The gradient of g is quite simple. It's just I plus 2j plus 2k. All right, so I know my two gradients. That's the calculus portion of the problem. I set the gradient of v equal to a multiple of the gradient of g, and this will yield our system of equations when we throw in the constraint. Here's the system. Equating the I components, yz equals lambda. Equating the j components, xz equals 2 lambda. And then xy equals 2 lambda as well when I equate the k components. And the constraint, again, is x plus 2y plus 2z equals 108. Well, it's algebra time. It's not so bad here. And that means I'll probably do it. Yeah, so let's do this algebra. Here we go. From the second and third equation, you have xz equals 2 lambda and xy equals 2 lambda. So they're equal to each other. Xz equals xy. Cancel the x's, and we get the key fact that z equals y. And again, by symmetry, you probably already knew that. So we know what z equals y. Let's keep going. From the first and third equations, we have yz equals lambda and xy equals 2 lambda. So if I multiply that first equation by 2, I get 2yz equals 2 lambda equals xy, and I can cancel the y's and get that x equals 2z. So now we have everything pretty much. We've got y equal to z, x equals 2y equals 2z. So let's finally use the constraint equation, which we haven't touched yet. That equation was x plus 2y plus 2z equals 108, and plug in these values. X is equal to 2y, so I replace x with 2y. I leave the 2y itself in the second part of that sum. 2z equals 2y because y equals z. That adds up to 6y, and the constraint was equals 108. Divide by 6, y is equal to 18. Wow, we got the answer for y. X is equal to 2y, so it's 36, and z is 18. So we have the answer by Lagrange multipliers. The dimensions are 36 by 18 by 18. And you can check your answer. It fulfills the constraint that the length plus the girth, x plus 2y plus 2z, indeed is 108. Well, what's the volume? This employee that's using Lagrange multipliers, did she get even a better answer? Well, let's see what her volume is. It's x times y times z, 36 times 18, 11,664. That's quite a bit bigger than 10,584 and 10,800, which the other two employees had obtained. So Lagrange multipliers, pretty powerful technique in this optimization problem. All right, let's go back to our opening example, which I modeled by looking into a lake and seeing that a fish might be in a different position than you think it is. The rule was as follows. When light travels in a transparent medium and it strikes the surface of a second transparent medium, the light waves tend to bend. They tend to bend in order to follow the path of minimum time. And this tendency is called refraction and is described by Snell's law of refraction that we saw at the beginning of this lecture. Again, let me set up the picture here of what we're going to study. We're going to have a person up there at position P in medium 1 and an object down in position Q in medium 2. And the light goes from P, strikes the boundary of the two surfaces, which I'm calling L here, at position O, and then it continues down to Q. And then if you draw the vertical through O, we have the angle theta 1 and theta 2 as labeled in the diagram. Furthermore, the distance x and the distance y vary here. Because it depends on where the light hits. But the sum, x plus y, is a constant. We'll call it a. Let's call the distance from P down to L d1 and the position from Q to L d2. So Snell's law, we saw that law at the beginning of the lecture. It's named after Willibrord Snellius, who lived from 1580 to 1626. He was a Dutch astronomer. But this law was actually known earlier by Ibn Sahl in Baghdad back in 984 when he was working on lenses. Snell's law is often called the law of refraction. And here's how the setup goes. We have v1, the velocity or the speed of the light in medium 1, and v2, the speed in medium 2. And I've already said that those distances d1 are labeled as in the diagram, and the angles are the angles with the vertical. And of course, x plus y is a constant. That's going to be our constraint equation. So what's the distance from P to Q? Well, according to the diagram, I have a couple of right triangles. The distance down to the line L will be d1 squared plus x squared. That, and then square root that. That's the length of the hypotenuse from P down to O. And then the other distance is d2 squared plus y squared. So that's the distance from P to Q. Now, speed is equal to distance divided by time. For example, speed is miles per hour, distance divided by time. That means time is equal to distance divided by speed, just multiplying through time and dividing by speed. This is what we want to minimize. We want to minimize the time that this light wave takes from going from P to Q. So it's time that we want to minimize, distance over speed. Well, the distance was that radical d1 squared plus x squared square rooted, and the speed there is v1, so I take that radical and divide it by v1, plus the radical d2 squared plus y squared, divide that by v2, and that is our time equation. Time is a function of two variables, x and y, because the point where the light wave hits L varies, depends on what x and y are. And it's a function of two variables, and there it is. But there's a constraint. G of xy, x plus y, has to be a constant a. So this is a perfect problem for Lagrange multipliers. We have a function that we want to minimize here. We want to minimize the time, not maximize it, minimize the time, and there's the formula for it, subject to that constraint. In this formula for t, all the quantities are known. d1 and d2 are given to us. There's certain distances, and v1 and v2 are the speed of light in the various media. The unknowns are just x and y. All right, how does Lagrange multipliers step in and solve this problem? Well, what's going to be kind of interesting here is when we do the Lagrange multiplier technique, you'll see that the answer, Snell's law, kind of pops out as a surprise at the end. It's kind of a surprise the way this works. You'll see it in a moment. But let's go through the steps of Lagrange multipliers. We need to minimize t, so we take its gradient, and that's going to be a multiple of the gradient of g. All right, and g is x plus y equals a. And of course, that means the gradient of g is pretty simple, I plus j. The gradient of g is the partial with respect to x, which is 1, and the partial with respect to y, which is also 1, so it's just I plus j. Pretty nice gradient. The gradient of t, not quite as pleasant. We have to do some calculus here. T is equal to that radical d1 squared plus x squared over v1 plus the other term. What's the partial of t with respect to x? Well, the y part doesn't have, its derivative is 0. So all I have to do is differentiate that radical divided by v1. So the answer would be 1 over v1, and then the derivative of that radical is 1/2 d1 squared plus x squared to the minus 1/2 power times the inside derivative, I'm using the chain rule, 2x. The 2's cancel, so we get the partial of t with respect to x to be x over v1 square roots t1 squared plus x squared. And in a similar fashion, you can do the partial derivative with respect to y, and you get basically the same answer, but now x is replaced by y. You get y over v2 square roots d2 squared plus y squared. Whew, that took some work. That was some heavy lifting calculus. All right, but now we're in good shape. Now we have gradient of t equal lambda gradient of g, and we know all our partial derivatives. We know our gradients. So the gradient of t is x over v1 times that radical, I, plus y over v2 times that radical, j, and that equals the gradient of g times lambda, which means it's equal to lambda I plus lambda j. Well, that's pretty sweet. That's a pretty nice result. That says that t sub x is x over v1 square roots d1 squared plus x squared, and that equals lambda. In other words, the component with the I components are equal to each other, and the j components are equal to each other, so the y over v2 square roots d2 squared plus y squared also equals lambda, and x plus y equals a, the constraint. Well, some magic occurs here. Let's look at this equation x over v1 square roots d1 squared plus x squared equals y over v2 d2 squared plus y squared. Those are both equal to lambda, so they're equal to each other. Well, look back at the figure. What is sine of theta 1? Well, theta 1 is the angle made with that vertical through O, but it's also the same as the angle over at P, right, in that triangle. And the sine at the angle at P is opposite over hypotenuse, so it's x over the distance from P to O. So sine theta 1 is x over square root d1 squared plus x squared. And in a similar fashion, sine of theta 2 is y over square roots d2 squared plus y squared. Isn't that interesting? So let's equate these now. We know that x over v1 square roots d1 squared plus x squared equals y over v2 square roots d2 squared plus y squared. Well, but that on the left, we have sine theta 1 is the x over the radical part, and then there's a v1. So we have on the left sine theta 1 over v1. That the left-hand side simplifies to sine theta 1 divided by v1. And the right-hand side simplifies to sine theta 2 over v2. Voila! There is Snell's law. Sine theta 1 over v1 equals sine theta 2 over v2. As I said, it was kind of magic, wasn't it? It just popped out using some trigonometry and using that figure. It just popped out. Wow, okay. Let me do an example with Snell's law, a fishing example now. As I said, I'm not a great fisherman, but I have been on a boat and observed that phenomena that the fish is in a different position than I think it is. And we can actually set up a little example here. Snell's law says that sine theta 1 over v1 equals sine theta 2 over v2. And if you solve for sine theta 1, you get it equal to v1 over v2 times sine theta 2. Okay, so that's an interpretation there of Snell's law. Now suppose light is passing from air to water, just like on my fishing boat. My eyesight goes into the water there. Well, there's an index of refraction for this situation, and that index is the value of v1 over v2. And it's approximately 1.33. You can look it up in tables. They have all these indices of refraction going from one medium to another. And for air to water, it's about 1.33. Okay, so here's our situation. I'm sitting up in my boat, and suppose I make an angle of 35 degrees with the vertical, and I look down, and I think I see a fish there, but it's really closer to me than I thought. Let's see how much closer it is using this equation. Well, we're assuming here that theta 1 is 35 degrees, so it's 35 going down to the water. Our formula said that sine of theta 1 is V1 over V2 sine of theta 2. And V1 over V2 is that index of refraction, about 1.33. So I have sine of theta 1 is 1.33 sine of theta 2. So I know what theta 1 is, 35. What I don't know is theta 2, the angle in the water. So let's solve for sine of theta 2. That would be sine of theta 1 over 1.33. And now you get out a calculator and you compute the sine of 35 degrees. And that's some number divided by 1.33, and you get some other number. Well, now what do? You know that the sine of theta 2 is this number. What's theta 2? What do you do now? Oh yeah, you have to take the inverse sine, don't you? Another key on your calculator. So you take the inverse sine of that number, and it turns out to be about 25.5 degrees. So if you look back at the picture, it's really kind of neat, I think. The angle is 35 degrees, and then there's a bending to about 25.5 degrees going from air to water. Nice example. I think Snell's law is really neat. I remember studying it in physics courses, but I never thought it could be actually derived using Lagrange multipliers. I hope you've enjoyed these 2 lectures on Lagrange multipliers. A very powerful technique, and we only looked at some fairly straightforward problems. It generalizes to many, many constraints, and that's when it's particularly powerful, when you have an optimization problem with 1, 2, 3 constraints, and as many variables as you want. We saw that we've had problems with 3 variables, and we can just go ahead and do them. The bad news is, of course, the algebra can be messy. I did a problem today where the algebra wasn't too bad, and you saw that it even took a little bit of time to do. Other problems can get quite difficult here. The key equation for Lagrange multipliers is the gradient of the function you're trying to optimize, gradient of f, equals lambda, a multiple of the gradient of the constraint equation, gradient of g. That's the key equation. That gives birth to some algebraic equations, and then you throw in the constraint equation, and you have enough equations and unknowns to be able to solve it. Again, it might have multiple solutions, although we haven't seen examples like that here. I have some exciting news. We're now turning to a new set of lectures on a pretty much brand new topic. You'll remember in elementary calculus that you studied derivatives, and then you moved on to study integrals, the inverse operation of differentiation. Well, we've spent a lot of time in our multivariable calculus studying partial derivatives, directional derivatives, gradients, optimization, etc. Well, now it's time to turn to integrals. How are they related to the differentiation processes in multivariable calculus? And in fact, how do you even develop integrals for multivariable calculus? Well, we'll take it fairly slowly. We'll develop double integrals. We'll see some polar coordinates here. And then we'll move to triple integrals. An integral, another integral, and another integral. And it gets even more exciting. We have integrals defined on curves in space, integrals defined on surfaces. So I'll see you next time when we begin our discussion of integration with inside multivariable calculus.